Okay. So this is not about the bias directly. It's about the clustering of cold dark matter and some analytic approach for it. The reason that it's related is that this approach presumably always claimed to be able to reach to very, very nonlinear scales. I will show you that it's not really the case, but nevertheless, the approach might still have something interesting to say. This will be the opening positive suggestion at the end. So this work started when Matthias Bartelmann visited Johns Hopkins a few months ago, and he showed us this quite amazing plot of a power spectrum. The blue curve is the Peacock and Dodds fit that is close to n-body simulations. It's not directly compared to n-body simulations, but it's close to it. And then this line is what they got with their model, and it was really just very simple one-loop integrals. Okay, and so of course this triggered some curiosity how this actually works. So what was emphasized heavily in the papers is the method, which is not usually a very good sign. So what they do is that they define, well, I'll explain why. I'll make this statement clear. They define some generalization functional from which they extract correlations using some quantum field theory tools. The physical idea, though, which is hard to obtain from these very long papers, is that instead of perturbing in the density field, the velocity field, what they do is that they perturb in the gravitational interaction. This is the key. That's what I mean by that. You don't sell something for the method, you sell it for what's the physical perturbation scheme. So this is the physical perturbation scheme. And so in this scheme, since you don't perturb in density, velocity, etc., stream crossing is not an issue in principle. Okay? I'll make this clear. Yeah, the perturbed trajectories and the perturbation parameter is a gravitational interaction, just like you would do in particle physics, where a particle interacts and you consider this as a perturbative interaction. Sorry? I'll explain. So what I do in this paper is to rederive this without quantum field theory, because it's kind of an overkill. So you just start with Newtonian trajectories, okay? Just standard Newtonian trajectories in an expanding universe. Just later on, this is a super conformal time, just an integral of the conformal time. You can write down an implicit integral solution. The trajectory at some time eta is just some initial condition piece, plus some integral along the trajectory of the gravitational potential, well, the gradient of it. And you need some initial conditions, so you can take the Zeldovich approximation at some early enough time. Okay, the usual, some Lagrangian coordinate, which is uniformly distributed, and then some displacement field, whose divergence is minus the linear density field, which is assumed to be Gaussian. And the velocity field is just the growth factor, linear growth factor times this displacement field. So the trick, I'll explain later on what is the actual small parameter. But for now, I'll just put in some bookkeeping parameter, epsilon, every time the potential appears. And then I'll just expand in epsilon the trajectories to 0th order in epsilon, which is just this piece. Okay, give me some initial conditions. I just move trajectories on straight lines. This looks very much like the Zeldovich approximation, except that it's not the linear growth factor that appears here. It's this free trajectory, free Hamiltonian propagator, as they call it in the paper. And then you have a first order, et cetera, et cetera. The first order is just simply obtained by computing the potential here that results from the 0th order. Okay? And how do you get the potential? You get it from the density by integrating over the streams, just like you do in Lagrangian perturbation theory. And then you expand this in epsilon, and it's slightly messy, but it's just algebra at that point. To go beyond first order, so this has I think the merit of being very clear of what's going on. If you want to go beyond first order, it's easier to just use directly the Boltzmann-Vlasov equation to write in the most general form. And by the way, Svedlin Tassev did something very similar, but starting from the Zeldovich trajectories, which is actually more accurate than this stuff, as you will see. So if you go through all the algebra, I'll show the result. I know people in this room are not scared of equations, so it's okay. So you can expand the power spectrum to first order, or to any order you want, but here I went to first order in this gravitational interaction, in this fake parameter epsilon. I'll explain what this epsilon really is in a minute. The first term looks exactly like the power spectrum you would get in the Zeldovich approximation, except that you replace this alpha, instead of being the linear growth factor, is in this case this propagator in the free theory, okay, which is smaller, as I'll show you later on. It's always smaller than the linear growth factor. But this looks exactly like the Zeldovich. Well, sorry. It looks what you would get if you took the Zeldovich approximation as a prescription for the trajectories. The first order term is some nasty looking integral, time integral, one loop, some double Fourier transform of some exponential. And if you think you can do these integrals, please let me know, because I spent several weeks and I cannot do this numerically. And I'll show you in a few slides how you get back the results of Bartman et al. From these integrals. So how does this approach? So we cannot do, I couldn't do at least, this integral, the fully nonlinear regime, where it would be interesting to see how this fares. How does it fare on large linear scales? So on large linear scales, I know that I can use the fluid equations, okay, for the density field and velocity divergence. I just start with these equations, and again, I'm going to put in an epsilon bookkeeping parameter in front of the gravitational potential. I write down an explicit, well, really an implicit integral solution for the density field at time eta as an integral of the previous time gravitational potential, hence density field. And then I expand delta in a series of epsilon. And because this equation is actually very simple, we know the solution is just a linear growth factor. And you can actually explicitly write down the full solution to arbitrary order in epsilon, which is just some time-ordered exponential of some propagator or Green's function times this is the linear, sorry, this is the 0th order free propagator of the theory. This is what replaces the linear growth factor. And f star is just the linear growth factor at the initial time. Okay, and so at infinite order, this is, of course, just the usual linear growth factor. But what I'm just emphasizing here, and it's kind of a redundant thing, a circular thing, that to get the usual linear perturbation theory, and by linear I mean linear in delta, one has to go to infinite order in the perturbation in this approach. I mean, basically, linear theory is solving these coupled equations without epsilon. So if you plug in an epsilon to get the correct solution, you have to go to epsilon to infinite order. That's all. So how does it work? These are the various linear growth factors at various orders in the epsilon, in the perturbation parameter, in the potential. So at epsilon equals 0, if you start, it depends on the starting point of the starting redshift. And I'll explain why again. If you start at redshift 100, it takes a really high order to converge to the full usual linear growth factor. If you start at redshift 10, then at third order, you're getting converged at redshift 0. But you still have to go all the way to third order. So coming back, so for the take-home message here is that for large scales, the standard linear scales, one has to go to high orders or apply this theory over a small interval of time to get an accurate result. For nonlinear scales, remind you the results to first order in interaction, which I cannot compute like this. How do you get back the results that were in the paper, the original papers? First, you have to expand to second order. Yes? I will say what epsilon so far has been just a bookkeeping parameter. I haven't defined what the small parameter is. I'll tell you what it is in a minute. Epsilon is 1. Epsilon is 1. It's just a fake parameter. Oh yeah, exactly. Yes, I just took 6 exponential. That's all there. I mean, it's just a fancy form of writing a bunch of integrals, of method integrals. So if you expand it, so this is the correlation tensor of the displacement field at the initial time. If you expand to second order, this correlation tensor, but not in its variance at zero separation, which is not self-consistent. Second, what they do is they replace this exponential term by 1/1 plus the variance squared times k squared. Not that I understand. Exactly, they take this way beyond. And then there's the question of what time do you start applying this method. What they say in the paper is that they determine the starting time by some consistency relation that matches the usual growth factor on linear scales. But as I showed before, you always systematically underestimate the linear growth factor. So I don't know how it is started, but I asked Matthias Bartelmann and he said it was a redshift about 10. So if you do all these, then it seems like you get the figure that they show in the paper.
The statement is only dependent.
Yes, in their paper they say that it comes from some self-consistency relation that does not require any other parameter. I don't understand really how this comes about.
If my initial condition is very, very, very low,
then it doesn't work.
High,
Yeah, no. Yes.
Probably not CDM or whatever at a particular scale.
They do this. They say that this is determined from large scales. But I don't know.
So basically, like this. So at one look, like they get this f2 delta squared, right? There is a k to the fourth. Basically, if you approximate the exponential as 1/1 plus k squared.
Yeah.
When k is large, it was like 1/k to the fourth. You cancel the k to the fourth on the f2, so you get something constant.
Exactly. So instead of, for example, the second paper is in the Zeldovich approximation. Instead of having an exponential suppression, as you get if you just take the Zeldovich trajectories, they get actually twice, and you can prove it.
Artifact of like this.
I think so. Yeah, I think it's an artifact. But I mean, okay. I don't want to be completely negative because I think there was some cute idea in using this interaction approach. But I think the actual result is not, it depends on these kind of ad hoc approximations. So what is the actual small parameter? So we know, where this is valid. So it's, grad phi times some time interval divided by the force, right? And then you work this out, and this is just Hubble times delta t. Okay, if you're in CDM universal. So this approach works only on small time steps. So the question would be whether this can still improve on, n-body simulations, because it's effectively like doing an n-body simulation. You can only take small time step. The difficulty is that, so the equations I showed you for the nonlinear power spectrum assumed a Gaussian initial condition. So you take the first time step, you're fine, and then at the other time steps, things become non-Gaussian and become more complicated. However, note that this would work, it does work, if you have a subdominant hot dark matter, for example, neutrinos. So now if I take what is the small parameter, and if I assume the grad phi is sourced by the CDM, and you can work this out, it's just free streaming scale over the wave number times delta m times h delta t. So even if this is 1, as long as k is much greater than k free streaming, and that delta m doesn't increase faster than k, then this approach will work. In fact, it does work. This is what Simeon Bird and I did in 2013. So what we do in this paper is that we compute the linear response of neutrinos to some gravitational potential, which is sourced by the cold dark matter in an n-body code. And so instead of following neutrinos as particles and using all the full power of n-body codes to follow neutrinos themselves and all the memory it requires, we can just replace them by a single integral, just by a linear transfer function from phi to delta nu.
First, just filter your CDM spectrum and then apply. You get something, just for that part, and then other part you do other ways. Is it possible?
For the CDM only, you mean?
Yeah, because you say this is good for HDF, because then you have the small scale cutoff. But then if I introduce that artificially from my CDM, will that work?
I don't know.
That scale,
I don't know.
that will.
It's not additive. It's not additive.
It's not additive here. Actually, that's the question.
So yeah, so this is showing the change in the power spectrum, the matter power spectrum, the total matter power spectrum with neutrinos or without neutrinos. Okay. Omega nu equals 0, omega nu equals some fraction corresponding to some sum of neutrino masses. And so the dashed line is linear theory, where everything is treated as linear. The red dash curve is the result from a code where neutrinos as well as CDM are treated as particles. And the blue curve is what we get with this method, where only the CDM is treated as particles and the neutrinos respond linearly to the CDM, and everything is evolved self-consistently. And so the agreement in terms of numbers at redshift 0, for the, again, this is for the total matter power spectrum, it's 0.2% for some neutrino masses of 0.3 eV, which I think is already marginally ruled out. And of course, if you increase the neutrino mass, it becomes a little worse. At redshift greater than 1, where this can be used for Lyman alpha force, for example, even for 1.2 eV, this works really well.
But isn't the contribution from neutrinos very small? Small to CDM.
The contribution for neutrinos to
Well, the total potential.
yeah, of course, yeah. Which is why it works very well.
Yeah,
Even if
maybe is that 2% just mu or and CDM on the scale? Just how does that compare?
Yeah, I mean,
no, whoa, sorry. So this is 20% because there are neutrinos. Even though neutrinos have a very small contribution, because you're comparing a universe where on small scales everything clusters to a universe where only some fraction clusters, and because it's nonlinear, it depends on it more. So in linear theory, this is 8 times the fraction of neutrino, and in nonlinear theory, it's like 10 times or something like that.
What kind of matter composition you're talking about here? Neutrino, how large a fraction, or you have?
So this is like something like 1%, 1 or 2% of the dark matter at redshift 0 is neutrinos. Right. For I think for this mass. And this is the total density field, which is the dark matter, the cold dark matter, and the hot dark matter.
Why is that? Because you say this actually it's only accurate for HDM, but as soon as you have CDM, then you have.
Oh yeah, no, the CDM is still treated with an n-body code.
oh, okay. Right, but
Okay, it's
would
only
you get
the.
pretty much the same result if you just treated neutrinos linearly? With also linear code?
I think you would get something that's not too far. No, I think so. I think the reason is that, as you said, the main effect. So I'm going to show next slide. So this doesn't get the neutrinos quite right. So this is okay. CDM, linear theory for CDM, neutrinos where everything's assumed to be linear. Neutrinos in our approximation, so they respond linearly to the gravitational potential of the cold dark matter. So this enhancement is just this enhancement. And this is what you get from a full n-body code where neutrinos are treated as particles. And we're missing a little something here. But because this is so much below, and on top of this you multiply by the fraction of neutrinos, it doesn't really matter. So I think, indeed, if you treated neutrinos completely linearly, you would be slightly less accurate. But and the reason you would be also slightly less accurate because you don't get the phases. Here we assume that neutrinos have the same phases as the CDM, which I think is more accurate than keeping the linear theory phases. But you would be pretty close. Yeah, basically, yeah. And so CDM doesn't bend little; it bends a lot. But over small time scales, then you can take a small bending angle. You treat it self-consistently. You just, you just have the Poisson equation sourced. So you have right, and then delta nu is some at time t is some integral, some Green's function of phi at previous times. And for CDM, you just use the delta CDM is n-body.
That n-body also take into account the mass of the neutrinos, the back reaction, everything.
Yes, so at any given time step, you estimate phi from the current delta nu and delta CDM, and then you get the next delta nu from all the previous phis, and you get the next delta CDM from the current phi and the current, and the velocity field, etc. So you do it self-consistently. Oh, sorry, yeah, thank you, very good question. So the whole reason why this is also better is that this is just shot noise. So you use all the n-body memory and power, and at the end of the day, unless you take a really large number of neutrinos, at high Ks you're actually much worse than what we do here. Because
Using n-body, yeah.
So, sorry? Using n-body, yeah. Anyway, so yeah, that's it. So take-home messages. So I don't want it to have appear too negative. I think it was a cute idea to use, instead of using perturbing in delta velocity, you could try and perturb in the interaction. And this, as Urosh mentioned, stream crossing is the biggest limiting factor of all the standard perturbation theories. In this case, it's not an issue. Okay, you can just, even if at 0th order, you take particles that have some initial displacements, some initial velocities, and you can just compute the density field. You don't care about stream crossing. This is only accurate and really meaningful once your actual perturbation parameter is small. And that is for cold dark matter over timescales which are short compared to the Hubble timescale. Or it does work for hot dark matter as long as the free streaming scale is larger than the nonlinear scale, essentially. So I showed you how it works, how it converges on linear scales. I cannot, again, if someone thinks they can do these integrals very easily, I'd be happy to see the results. It would be nice to see how it converges on nonlinear scales and to study in detail how small the time step has to be and stuff like this. So yeah, it's definitely not the panacea of large-scale structure as it seemed to be promising, but maybe it could be useful to replace some steps of n-body simulations or something.
Great, thanks.
That's it.